Math 1332, Chapter 2, Set Theory, Section 2.2, Subsets and Set Operations, Video 6, Intersection of Two Sets. All right, it's time to define some set operations. And to be clear what I mean by operations, in math, an operation is a process that you perform on one or more objects to turn it into a new object. You're already familiar with a lot of operations when it comes to numbers. For example, if I gave you the number 2 and the number 3 and I put this operation between them, it's going to make a new number. I think you know that number would be 5. An operation that turns two objects into a new object is called a binary operation, bi meaning 2, and you're familiar with several binary operations. For example, 8 minus 2 is a binary operation. Its difference is 6. But 8 times 2 is also a binary operation. Its product is 16. 8 divided by 2 is a binary operation. Its quotient is 4. But there are operations that only operate on a single object. For example, you may know what this symbol is, and you may know what the answer to the square root of 25 is. The answer to the square root of 25 is 5, because 5 squared is 25. But an operation that only requires one number is called a unary operation, as opposed to binary, because the prefix un means 1, bi means 2. So an operation, again, is just a process that turns one or more objects into a new object of the same type. We've already actually seen one unary set operation, and that would be complement. You only need one set to find its complement. Granted, you need it in the context of a universe. But intersection is an example of a binary set operation. So let's get right to it. We start by letting A and B be two sets. So we're going to take two sets. Then their intersection, which is written this way, the symbol for intersection looks like an upside down capital U. That one's not drawn too well, but if I were to redraw it, it would look something like this. That's the symbol for intersection. Kind of looks like a lowercase n, as in intersection. But their intersection written as this way, and you can read that as A intersect B as a verb instead of a noun. A intersect B is defined as the following. Here's its rigid definition, and then we'll give it a little bit more clarity. It's the set of all x's, so we're gonna define it in set builder notation, such that x is an element of A, and, emphasis on the word and, x is an element of B. So let's do a visual real quick. Let's say that you have a room full of people, and you ask them, raise your hand if you were born in Texas. And some of the people raise their hands. All right, hands down. And then you say, raise your hand if you're female, whatever you want to interpret that as meaning. I interpret it in the biological context, but that's just me. Raise your hand if you're female, and then some people raise their hand. And then they say, raise your hand if you were born in Texas and you were female, and somebody raises their hand. What do you know about that person? They were born in Texas and they were female. They belong to both sets. They belong to both groups of people that raise their hands. That's the intersection. The intersection is just elements that are common to both sets. Visually, the intersection of two sets is the set of elements they have in common. That's the important phrase, the set of elements that they have in common. All right, so why is it called intersection? Well, we'll see when we get to the Venn diagram aspect. But before we do that, let's just take a look at a few examples. For these examples, we're going to use the same 4 sets. We're going to use a universal set of the numbers 1 through 20. So these numbers here. And in that universe, we're going to have set A, which contains the numbers 1 through 10. Set B is going to contain the even numbers in U. So 2, 4, 6, 8, 10, 12, 14, 16, and 18. And I've written C in set builder notation, the set of x's such that x is an element of the universe and x is odd. So really it's just like B, except it's the odd numbers. All right, now if it helps, you can list out the elements of B and C so that you can visually see what they're made of. We'll do it over here. B contains the even numbers, so 2, 4, 6, 8, ... 20. I know I'm writing them out, and at the same time, I'm not writing them all out. And C contains the odd numbers, so 1, 3, 5, 7, and that one would end with 19. All right, so let's find some intersections, starting with A intersect B. To find A intersect B, we have to look at set A, which I'm highlighting now, and set B, and locate the numbers that they have in common. Well, what's one number they have in common? 2. What else? 4. Any more? 6. 8. Is there anything else they have in common? Yes. The 10, which is implied by the ellipses, is in there, which is why maybe we should have written out all of them. But are there any more numbers in common? The answer is no. Because in A, the remaining numbers are odd, which are not in B, because B contains even numbers. And in B, the remaining numbers after 10 are greater than 10, which are not in A, because everything in A is 10 or less. So the only numbers they have in common are 2, 4, 6, 8, and 10, and that would be their intersection. So the intersection of A and B, we'll put the answers in red, are 2, 4, 6, 8, and 10. We've made a new set from 2 previous sets by finding what they have in common. Let's look at A and C. Set A still contains the numbers 1 through 10. Set C contains the odd numbers up to 19, because remember, our universe stops at 20. What is their intersection? I invite you to pause the video and see if you can write it down. I'm going to be highlighting them here in just a moment. All right. They have a 1 in common. They don't have a 2 in common, but they have a 3 in common, and a 5, and a 7. Anything else? The 9. The 9 is implied by the ellipses. We could write out a couple more elements to locate it, but that's all they have in common. The only numbers remaining in A are even, and C contains no even numbers, so they can't have anything else in common. So their intersection is the set containing 1, 3, 5, 7, and 9. Let's write that down. All right, so there's the intersection of A and C. What about B and C? B contains, well, the even numbers. C contains the odd numbers. So what do they have in common? Trick question. They have nothing in common because, well, the numbers in B and even are even, and the numbers in C are odd. And a number can't be odd and even at the same time. So it seems like they have no intersection. But I have to answer the question. So let's open up a set. What should I write in it? Nothing, because they have nothing in common. So as soon as I open it and I can close it, their intersection is empty. There is a word for 2 sets whose intersection is empty. And I may use this word in the future, so I'd owe it to you to warn you about it right now. So note, 2 sets whose intersection is empty. Which means they have nothing in common, are called disjoint. And again, I may use that word in the future without thinking twice about it, like I used the 3-dot triangle for therefore previously. But 2 sets that have nothing in common, that have an empty intersection, are called disjoint sets. All right, let's try the last 3. U intersect A. Remember, the U is the universe here. So let's highlight U and A by getting rid of these highlights here. Oh, not that. There we go. All right. Here's the universe, everything from 1 to 20, or all natural numbers from 1 to 20. And here's A. And what do they have in common? Well, the universe contains everything, so it contains all of this. And so what they have in common is everything from 1 through 10. But wait a minute. Isn't everything from 1 through 10 Just set A? Yeah, the intersection of the universe in set A is set A. It's the set containing 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I could list the answer in roster form, but that's just set A, so we might as well call it what it is. The universe intersect A is set A. What do you think the universe intersect B is? Here's the universe, here's B. Well, everything belongs to the universe, so everything in B is also in the universe. 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. So just like before, the intersection of the universe and B is set B. So we can just write universe intersect B is set B. Let's get rid of that and draw it. And using a similar argument, the universe intersect set C is C. There's another generalization we can make here. For any universe, and you may have noticed I've been saying universe instead of universal set. They're kind of synonymous. And any set, we'll call it X, inside of U intersect X is equal to X. We're going to draw the intersection symbol inside of there. Give me 1 second. There we go. So if you intersect any set with its universe, you get that set back. All right, I'm going to pose one more question here real quick. As soon as I can get it to draw what I want. Okay, here we go. How about A intersect the empty set? Well, here's A. We know where set A is. But what does the empty set contain? Nothing. So what would they have in common? Well, nothing, because the empty set is empty. Meaning that A intersect the empty set is the empty set. And you can actually say that for any set. Any set intersect the empty set is the empty set. All right, I'd like to wrap up this video by showing a Venn diagram for intersections. And because we have 2 sets, we need 2 circles. But the way I have this Venn diagram set up so far is not good. Before we get to the Venn diagram, let's figure out what this intersection is by looking at sets A and B and seeing what they have in common. Here's A and B. Do they have anything in common? Not much. I take that back. They have 3 things in common. They have a 3 in common, a 5 in common, and a 7 in common, which means the numbers 3, 5, and 7 need to be inside of circles A and B simultaneously. Let's go ahead and write the intersection over here. 3, 5, and 7. However, notice that A is not a subset of B, because A has something that B doesn't, like 1 and 9, and B is not a subset of A, because B has something that A doesn't, 2. So I need the numbers 3, 5, and 7 to be inside of the 2 circles simultaneously, but I can't just put one circle inside of the other. So how do we fix that? Easy. We take these circles and we make them overlap. By making them overlap, but not putting one inside of the other, we've provided a space to put the numbers that belong to both of them, namely the intersection. So let's put in the intersection numbers. The numbers 3, 5, and 7 have to belong to both circles at the same time. That would be the little football region in the middle. But let's put in the rest of the numbers in the universe, starting with the number 1. The number 1, which I'm going to highlight in yellow, is clearly inside the universe, but it's also inside of set A, but not set B. So where should I put the number 1? Can I put it here? No, because it's not inside of circle A. Can I put it here? No, because it's still not inside of circle A. Can I put it here? No, because although it is inside of circle A, it's also inside of circle B, and 1 is not an element of B. I have to put the 1 in this left region, this left moon shape, because I need it to be inside of circle A, but not circle B. What about the number 2, which I'm going to highlight in green? The number 2 belongs to set B, but not set A. So where in the Venn diagram should I put the 2? Right here. It's got to be in circle B, but not circle A. I'm going to do one thing real quick. We'll put that in yellow just for some consistency with the colors. All right. We've already placed 3, 5, and 7. So I'm going to highlight those in the universal set. We've already placed 3, 5, and 7 in the middle. Where would the 4 go? Let's highlight that in purple. Does 4 belong to A or B? No. So it can't go in either circle. So where would the 4 go? Outside of both circles, but still in the universe. As would the number 6, and the number 8, and the number 10. Notice that those don't belong to A, and they don't belong to B either. So they have to be outside of all those circles. So 4, 6, 8, and 10 have to live in the universe outside of the circles. The only number we have left is the number 9, which is in set A, so we'll highlight it yellow just like we did the 1. And because 9 belongs to set A but not set B, it has to be inside circle A but not circle B, so it goes right there. Question, and I've already answered it. Which part of this Venn diagram represents the intersection? And the answer is the part in the middle. Try and get some highlighting going on here. One second, folks. The part in the middle where the circles overlap. Didn't mean to highlight it and make the numbers hard to see. But that part in the middle represents the intersection of A and B. Keep that in mind because in future sections, we will be talking about the intersection of 2 sets in terms of Venn diagrams quite a bit. All right, here it is.